now. If you want to count, remember the transition group starts from, according to IUPAC recommendation, starts from group 3 to group 12 over here. So let us take a look at the transition series and transition groups and their unusual or unique electronic configuration patterns. There are 3 transition series, namely the first, second, third, and fourth transition series. The first series, also called the 3D series, are in period 4, starting from scandium to zinc. Second series, also known as the 4D series, are in period 5, starting from yttrium to cadmium. Third series, known as 5D series, starts with the lanthanum and ends with mercury. The fourth series, 6D series, contains actinium and other elements, mainly artificial elements, discussed along with the F block elements. Here, I will focus on the first 3 transition series and the electrons present in the D subshell of their neutral atoms. So, let me show you the configurations over here. As you can see on the screen right away, okay, on the table, as you can see there, what we are going to do now is I will be giving you the number of D electrons. Over here, we will do our counting, of course. So we are going to be considering the distribution of electron, that's the electronic configuration in terms of 1s2, 2s2, how many electrons will be there. See how I'm going to do it. I'm going to count which is there on the screen already, but I will just repeat it again. I'll be counting in terms of maybe I'll be giving you 1, 2, 3. Now, if you want to count, remember the transition group starts from, according to IUPAC recommendation, starts from group 3 to group 12 over here. But remember that when we say group 3, without the transition metals, we refer to the aluminum group, which is actually, according to European, is the main group, 3B. Okay, but conventionally, IUPAC says we should number them serially. Now, look up here. We will be counting alongside, starting from scandium group. Scandium group means scandium, yttrium, lanthanum, and down to zinc group, which includes zinc, cadmium, mercury, and the other artificial elements I might not know. So remember that this is their D electrons. Over here shows their D electrons, meaning how the D electrons are filled. So while writing the configuration of scandium, it will end in ND1. That is this one here. So let's take a count. Assuming you are partying, you use the term, we are going to use one acronym, which will say no night, no fall. If you party around where you love what is happening in the party, you can confidently say no night, no fall, meaning no daybreak, no day party on, you know. So, but here, if you check from 1 to 10, which of the number rhymes like no 9, 9, 9, 9, no nights, no nights, which is 9, no fall, no fall, which is 4. So if you are counting for neutral atoms, we won't be considering 9, neither are we going to be considering 4. So there won't be anything like neutral atoms will not have ND9, neither will they have ND4 for neutral atom. N here is the shell, why D is subshell, that's the N is the principal quantum number, just like KLM, you know what I mean. So let us move on to clear you. The counting is already there, as you can see. So I'm going to count now. That's why I wrote that number, so that I don't get it twisted. 1, we move by having, counting is 1, 2, 3, 5, 5, 6, 7, 8, 10, 10. Instead of having, so I jumped 4. So no neutral atom is expected to have the 3D4 and then 3D9. These are exceptions that we will now consider when we write the configuration, which makes group 11 have some unusual configuration. In addition, with this group 6, according to IUPAC recommendation, that's transition group 6, chromium, molybdenum, have unusual configuration. Instead of ending in D4, they end in D5. So you should pay rapt attention very well in that of chromium, which is number 24. Chromium should be normally 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4 because it's number 24. Remember that scandium is 21, titanium is 22, 24, the vanadium is 23, and this is 24. So if you share electron, calcium is already 20. Looking at this, you're supposed to end in 3d4, but this is incorrect. From what I'm telling you now, we don't have 4, we don't have 5. Therefore, the correct configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, and 4s1. So this is the correct configuration of chromium. The same thing is applicable when you come to copper. Be careful. Copper in the correct configuration. Remember, what applies for chromium also applies for molybdenum, but not for tungsten. That's why I painted it pink. I will discuss that later. So, but when we come to copper, copper has 20 what? 29. That's copper should be number 29 and zinc should be 30, of course. You are not expected to write one normal thing that one should expect while writing copper is copper 29 should be 1s2. I don't want to use the noble gases to make it easier. I don't want to use the noble gases making it easier. So we have 2s2. I want to go in details. 2p6, 3s2, 3p6, 3, and then 4s2, 3d9. This is incorrect. So the correct thing should be what? 1s2, 2s2, 2p6, 3s2, 3p6. The D is filled before the 3D is filled before the 4s, which is unusual, 3d10 and 4s1. So this is our interest. This is where our interest lies. You see, this is 3d10 and 4s what 1 is a deviation. The same thing is applicable when you handle any other members of the copper group. That's copper, silver, and gold. But the other artificial element there, which is a rotangent, is exception. That's why I highlighted it on green. So this is unusual configuration of the period, the so-called D block what elements. Okay, one good thing about this configuration you're seeing here is that having given you these numbers, I've cleaned everything. Now you remember that when I said scandium, all these ones, all their configuration will end in D1. All these ones will end in D2. That's what it implies. Then the members of these ones will all end in D5. And these ones also, the coinage metals, the one we use for making coins, we end in D10 also, and the same thing with 12. So that's the significant. Now, the advantage is that the first series is called 3D series, and second is 4D, the third is called 5D, then the fourth series is called 6D. So let's assume I want to write the electronic configuration of molybdenum over here. This molybdenum, how will I know what will happen? Under here, how many electrons does it supposed to have? It's supposed to have 5 and is under 4d. So molybdenum will have 4d5. Now let's take vanadium, for instance. Look at vanadium is here. It will end, the last d subshell will be what? Is under 3d series. So I will write 3d. But how many electrons will it have? It has 3. 3d3. So that's the need for these numbers I gave you, which will help out, like the number for these shells and the names. They are 4D and 3D. Now, can you guess what will end that of a cadmium? Cadmium will end in what? You look at the position of cadmium. Look at it here. This is cadmium. So cadmium is expected to end in, from what I taught you, is under what series? Is under 4D series, and it has 10 at the end. So configuration of cadmium will end in what? 4D10. For this artificial element, look at mercury also. Mercury will end in what? Is under 5D series. It will end in 5D10. So the same thing, if you look at nickel, which is the only one that obeys it, where other ones I highlighted in different colors disobeys this thing I'm teaching. So if you look at nickel, nickel is in 3D series and the 3D electron is 8. Hafnium is in 5D series and the d electrons is 2, so it's supposed to end in 5d2. So that's the need of this table. So you have to relate these numbers to write the configuration of what is inside. Now, let us see the distribution of the electrons in the shell. Why we say that they transitioned from 8 to 18. Why do we even call them transition? Their electronic configuration gave them that name, but this is not the type that will give it. Remember, apart from these ones I mentioned here, every other one follows, which means ion here will end in 8. Ruthenium will also end in 8. Osmium will end in will end in 6, please. This is the d electron. The d electron will be 6. We are talking about the last d electron. But if there are, like, if an atom have 3d before 4d, we are considering only that 4d. The 3d will be completely filled, though, but their last d subshell will be partially filled. That is it, what we call transition elements. Okay.